So let's start. All right, so first, good morning, everyone. I hope you are doing well. My name is Roberto Rolo. I am a senior consultant at Geovariances-Datamine. And today we will explore what I believe is a very relevant and exciting topic in today's mining industry, which is machine learning applied to geoscience and mining. So let me give you a little bit of information about this webinar. So this webinar will last approximately 1 hour, including the presentation itself and a quick demo using Is-That-Is.Neo. At the end, we will have a Q&A session, so feel free to ask any question, and I will try to do my best to answer that. And at the end of the session, you will receive this recording via email. So before we explore the different machine learning algorithms and discuss how and when to apply them, I'd like to start with a discussion on the current state of machine learning, specifically in the context of resource modeling. I recently attended to the last Geostat Congress in the Azores, which is, by the way, an incredibly beautiful place. And we had a week full of amazing discussions and interesting presentations about geostatistics and, of course, machine learning. In fact, maybe there was even too much machine learning. When I searched the Congress program for geostatistics to include geostatistics and geostatistical, I found 24 results. But when I did the same for learning to include machine learning, deep learning, reinforcement learning, and so on, I found 23 occurrences. So it's clear that machine learning is becoming a major trend in research related to geostatistics and mineral resources estimation. And Professor Michael Prix brought a very interesting reflection during his keynotes in the same Geostatistics 2024. And I thought it will be valuable to share with you. So we all enjoy the recommendations made by platforms like Spotify or other music and video streaming services. But have you ever wondered how these platforms manage to predict what we'd like to listen or watch? So the secret here lies in leveraging billions of user interactions. So every time you play a song, skip a track, explicitly like something, or creates a playlist, they generate data. And this data will feed the machine learning algorithms, allowing the system to learn users' habits and preferences to suggest songs or shows that they might enjoy. And now, what is the cost of a wrong prediction? What happens if Spotify recommends you a song you don't like, or if Netflix recommends you a series or show, a TV show you don't like? Essentially, it's zero. If the recommendation is off, you would just skip the song and move on with your life. Now let's make a comparison with what we typically encounter in geology and mining applications. So unlike platforms like Spotify, where there are billions of user interactions, we often deal with far less data, hundreds of thousands of drill holes, an interpreted geological model, geological maps, maybe some geophysics. And additionally, we deal with a very particular type of data. It is sparse in X and Y directions, but highly dense in the Z direction. And clearly, this is not comparable to billions of interactions. And what about the cost of a wrong prediction? So in our case, is far, far away from zero. It could mean losses of thousands or even millions of dollars. So this is what makes machine learning for resources modeling so unique. We usually have limited data to work with, yet the stakes are incredibly high. And this dynamic highlights the challenge and precision required in applying machine learning to geological and mining problems. Before we actually start showing some applications and showing how to apply geostatistics together with machine learning in Is-That-Is.Neo, let's organize things with some definitions. So what is machine learning? Here's how Wikipedia defines machine learning. Machine learning, ML, is a field of study in artificial intelligence concerned with the development and study of statistical algorithms that can learn from data and generalize to unseen data and thus perform tasks without explicit instructions. I want to draw your attention to the phrase statistical algorithms. As its core, machine learning is essentially a sophisticated application of statistics. And this perspective is important because it demystifies machine learning. While it's often treated as an abstract, almost magical tool, the reality is that it's grounded in principles many of us are already familiar with, which is statistics and data analysis. Machine learning approaches are traditionally divided into three broad categories corresponding to their learning paradigms. So we have unsupervised learning. In this type of learning, the computer is presented with examples, inputs, and their corresponding correct outputs. In other words, the computer needs a teacher, in quotes, to learn a general rules that maps inputs into outputs. In unsupervised learning, on the other hand, the computer does not need a teacher. It learns by itself to identify patterns in the input data. In reinforcement learning, the computer interacts with the environment and must achieve a specific goal. As it interacts, the program provides feedback to guide the learning. So in the following steps, I will present the algorithms in each of these categories and explain how they are applied to mineral resources estimation. So in the following slides, we will explore unsupervised algorithms and their application in the context of resource modeling. So unsupervised learning can be categorized into different groups, one of which is dimensionality reduction. In this group, a notable algorithm is principal component analysis, or PCA. And the primary objective of PCA is to transform a correlated multivariate distribution into orthogonal and then uncorrelated linear combinations of the original variables. These components can assist in exploratory data analysis and also play a significant role in the estimation process. Since the components are uncorrelated, they can be estimated or simulated independently, and the results can be then back transformed to restore the original correlations. As an application example, I like to highlight a study by Professor Julian Ortiz and his team, where PCA was used to independently simulate correlated variables in a lateritic nickel deposit. Principal component transformation, PCA, that correlates data globally. However, in geostatistics, we work with spatially dependent data. And the objective of maximum autocorrelation factors, or MAF, is to incorporate the spatial component into the decorrelation process. So MAF decorrelates the data at a lag of separation h. So PCA will decorrelate the data for h equal to 0, and MAF will decorrelate to a chosen lag distance r. A notable application example can be found in the seminal paper by Switzer and Green. Multidimensional scaling, or MDS, is a technique designed to visualize and compare high-dimensional data. An application in resource modeling proposed by Clayton Deutsch and his team involves ordering simulations by similarity. And this approach allows for, example, selecting 3 or 5 most relevant realizations out of 100, which can then be used in the posterior processes. For example, in stochastic mining planning, for example, when we can't use 100 realizations, we can pick 3, 5, or 6 most important. There's a family of clustering algorithm within the unsupervised learning group. The objective of these algorithms is to group a set of objects so that objects within the same group, called a cluster, are more similar to each other than those in other groups. So in other family, we want to group similar objects in a cluster and make clusters that are different, the most different possible between themselves. This family includes techniques such as hierarchical clustering, k-means, dbScan, among others. Due to time constraints, we will focus on hierarchical clustering. This technique works by recursively merging or splitting data based on similarity. Then we summarize the results in a tree-like structure known as the dendrogram that we will see in the demo parts. It is important to note that these algorithms do not account for the spatial components of the data, which can sometimes lead to noisy and non-geological results. And as an application example, I would like to highlight the work of my supervisor, João Felipe, and my colleague, Gabriel, who they use various clustering techniques to define geological domains in a phosphate mine, and they also proposed the use of indicator variograms to validate the results. And to address the limitation of traditional clustering in geological contexts, geostatistical clustering algorithms have been proposed. Traditional clustering methods may produce results that are not geologically realistic, full of noise. So geostatistical clustering will add a spatial component to the analysis. Doing this, we ensure that the results are more consistent with the spatial connectivity of the data points. In this group of algorithms, we can highlight geostatistical hierarchical clustering, which extends traditional hierarchical clustering by considering spatial connectivity between data pairs. As an application example, I can mention the seminal paper. The methodology was developed by researchers from School of Mines in Paris, and this is available in ISERIS Neo, and we are going to have a look at this tool in a few minutes. So in the next slides, we will explore this time the supervised algorithms and their application in the context of resource modeling. Supervised learning is one of the primary groups of machine learning algorithms, and it is divided into two main tasks, regression and classification. Regression focuses on predicting continuous values. For example, in mining, we can use regression to predict ore grades based on various input variables such as location, geochemical data, geological features. On the other hand, classification deals with assigning discrete labels or categories to the data. In this context of mining, this can include tasks such as classifying lithological units or identifying geological domains based on well logging or sample data. Both regression and classification, they require labeled data for training, where we provide the model with input-output pairs, and the goal is to learn a general mapping that can be applied to new and unseen data. A general rule is that the same algorithms can be used for both regression and classification tasks. There are many supervised learning algorithms available. Some examples include k-nearest neighbors, linear and logistic regression, linear discriminant analysis, decision trees, support vector machines, random forests, and neural networks. These algorithms, they represent different levels of complexity, and each is suited for specific types of tasks depending on the data and the problem being addressed. In the following slides, I will present practical applications of these algorithms in resource modeling, similar to what we explored for the unsupervised ones. So Sansom and Clayton Deutsch, they used elliptical radial basis neural networks in combination with collocated kriging to estimate ore grades. So in the recent years, numerous papers with the objective of replacing kriging by some type of machine learning based estimations being emerged. You can find them in many different scientific journals, and the number of this type of publications is rising wildly in the recent years. My colleague, Fernanda Gontijo, and again, my advisor, João Felipe, they used neural networks to predict geometallurgical variables in a zinc mine. Hadavan and Deutsch, they use deep learning, a specific type of neural networks, along with lambda distributions to impute missing data using multivariate scenarios. Another one from Brazil, from my advisor, this time in collaboration with Felipe Beretta, involved flying a drone over the mining area. Then they use different machine learning techniques to classify the mining fronts into waste or vegetation and soil. Al-Zubaydi used convolutional neural networks to classify drill core samples from images. So they have a picture of the drill core boxes, and they use these machine learning algorithms to try to log it automatically. Smirnov used support vector machines for three-dimensional geological modeling from scattered data and geological modeled sections. Elga Jordão and Professor Amilcar Soares in Portugal, they used Bayesian neural networks for modeling geological boundaries and assess its uncertainty. So to wrap up this short presentation, we explored why the application of machine learning in our field is so unique. We covered the definitions of machine learning, unsupervised and supervised learning, regression, and classification. We also review some fascinating applications of various algorithms for tasks related to mineral resources estimation. And finally, I'd like to take a moment to invite you to our upcoming machine learning session. This is a training session, a 4-day training session, where we will explore in depth all of these methods. We will combine theory with hands-on practice using Is That Is New. And this course, the next one, will take place on April 14. But if you go on our website, geovariances.com, you can see the calendar for all of the trainings in the year. Now let's proceed with a quick live demo using Is That Is New to apply some of these machine learning techniques. Okay, so let's jump into Is That Is. Here we go. So for those who are not familiar with Is That Is New, this is, let me just remove this presentation. Okay, it looks better. All right, so this is the main window of Is That Is New. Is That Is New is geostatistical software. You will find all of the building blocks to generate simple and complex geostatistical workflows. The graphical user interface is quite familiar. I believe most of the mining softwares nowadays, they are quite similar to each other in terms of the visual aspects. So it's a ribbon-based software. On top, you will find the different algorithms grouped into different sections. Inside each of the sections, you have the tasks or the algorithms grouped in subgroups. So inside home, you have project, import, export, and preferences. And the same applies for every other big group. At the bottom, the graphical user interface is divided basically in two different regions. So we have the visualization window on the right-hand side. So here we can visualize every 3D element or 2D element. So you have 3D scenes and maps, and you can create as many maps, as many 3D scenes you want, showing different combination of objects on each of these tabs. Then on the left-hand side, we have the object sections. So here is where we'll store the different elements, the different objects that will build our projects. So we have a tab, a small vertical tab for the data. So all the data tree will show here. I mean, all the drill holes, all the polygons, all the wireframes, all the grids, all the polylines. So every data you import to your project, you will see it in the data tree. Then you have a tab for the geostatistical sets, and the geostatistical set is a very important type of object in ESETI's NEO context. It will store not only the variogram, but all of the statistical information related to your data. So the Gaussian anamorphosis, the trends, if you have it, the variogram. So it will carry a lot of information, and this is what we will input into the geostatistical algorithm. So the Kriging algorithm, we will expect a geostatistical set as input, as the simulation algorithms, and so on. Then you have the chart files group. So here is where we will store all the plots. So I'm not meaning maps and 3D viewers. I mean histograms, scatter plots, box plots, and all the types of figures, two-dimensional plots we can generate inside ESETIS. Then we have a group for the scenes. Now we are talking about maps and 3D views, so we can store different scenes in this region. We have a group for color scales, for catalogs, which are color scales for categorical variables, for search neighborhoods, for rotation conventions, and finally, the batch files. So in ESETIS NEO, you can script your workflow, and to script your workflow, ESETIS will use these files called batch files. These files are XML files, so they are very similar to an HTML file. And these XML blocks, they will store all the parameters that you will put in the graphical user interface. So in a batch file, you can combine different XML blocks representing the different tasks, so the variogram task, the rigging task, the model validation task, and so on. You can add flux control. As flux control, I mean you can add for loops to loop into different variables, different domains. You can add if-else conditions, for example, to make your workflow very flexible, automated. And you can also add Python blocks. So ESETIS NEO will come with a Python interpret pre-installed, and the most common packages for data science, which include NumPy, Pandas, SciPy, sklearn, Matplotlib, Seaborn. If you want to use an external package, it might be possible to install it in ESETIS, although it's not officially supported. To gain some time, I already created some batch files to show you how to apply machine learning together with geostatistics in a very hands-on manner for this quick session. So the first thing I'm going to do is to run my first batch file, 01 import, which will import my data. So here we have an import CSV. So we are importing a CSV file as points, and then we are importing a polygon. So I will run both, and I will show you the outcome. If you double click one of these tasks, you can see the graphical user interface with all of the inputs that you will put into the graphical user interface, but recording it and running in a batch file is exactly the same thing, but we are automating this step. So after running the first batch file, imports, we have in our data tree, data, a point set called data. And here we have 5 chemical variables: zinc, lead, copper, chromium, cobalt, and cadmium. We have 2 geometallurgical variables, metallurgical recovery and mass recovery, and 2 categorical variables, rock and land use. I would just drag and drop the zinc variable from the data tree to the map. So here is what we have. Some of you might be familiar with this data set. This is the Jura data set, the data set used as example for the Pierre Gouvaerts book, very good book in geostatistics. I will right-click on the zinc and ask for a histogram. So we have 259 samples for all of these 5 chemical variables. Now I will drag and drop rock, which is one of the categorical variables we have in our data set. So rock is quite the same thing. We have 259 samples in 4 different groups. 1, 2, 3, 5. We have 4 categories, 259 samples. And we also have these geometallurgical variables. Let's focus on metallurgical recovery. And let me ask for a histogram. And as we can see, we have 100 samples for this geometallurgical variable. Here, we are trying to mimic the usual environment we have in real mining applications. So we have multiple variables. Sometimes they are sampled in the same location. So it means that the data set is isotopic. So we have all the variables in all of the samples. This is our case here. And we have the geometallurgical variables, which are usually way more expensive to produce. It requires some geometallurgical bench tests. So usually we have less geometallurgical data compared to chemical variables. And on top of that, specifically for geometallurgical variables, we have 2 additional issues, 2 additional particularities. The first one is that usually geometallurgical variables, they are not additive. It means that we cannot estimate using Kriging because they do not average linearly. So if you use Kriging to estimate a non-additive variable, like geometallurgical variables in the majority of times, your models will be biased. And the other particularity or the other issue is that usually we have way less samples in comparing to chemical variables. So usually we cannot calculate and model a reliable variogram. Our estimates will be made with very, very, very sparse data, and we cannot trust these estimates as we trust the estimates for the chemical variables. So this is why usually machine learning is used in the geometallurgical variables modeling context to try to tackle these 2 particularities. And this is what we are going to do here. One of the tasks we are going to do here, we are going to do different things using machine learning. One of them is trying to model this geometallurgical variable, but not by estimating or simulating it directly, because we only have 100 samples, it's not enough. And so we are going to obtain them indirectly from the chemical data. All right, so next thing I'm going to do here is a quick EDA. So I'm running this, and I will double click this calculator to discuss a little bit the calculator, since it's a very important, not only is that is NEO task, but this is a test, this is a tool that it will be very, very useful and important if you want to perform this kind of geostatistics and machine learning workflow. So the calculator, as the name suggests, is a calculator. And the objective here is to grab information. So we can grab all of the variables from our project. And we can do any type of calculation, any type of manipulation with these variables. For those who are familiar with ESETIS Classic, I mean the last version of ESETIS, not ESETIS Neo, the calculator already existed at that time, but the calculator used proprietary programming language. And now in ESETIS Neo, the calculator will use Python. So you can use all of the Python functionalities inside ESETIS Neo seamlessly. So here in this calculator is a simple one. We are just reading the variables. We are importing pandas, seaborn, and matplotlib, and we are performing a correlation matrix plot. We want to check the correlation between all of the input variables because the correlation is very important in the machine learning context, but I will discuss this later. But let's have a look on what we have here. So inside the project folder, we have this public folder, which is the folder intended to store all of the information generated during the workflow. So here inside the EDA, we have this correlation matrix. Let me put this into this monitor, right? So we have this correlation matrix that shows the correlation between all of the variables in our data sets. And remember this will be very important, and we will discuss this a little bit later. Okay, now let's start applying machine learning algorithms. I will start by applying some clustering algorithms to our data, and let's discuss the results. And after that, we will apply the supervised techniques with regression and classification. So let me double click the batch file clustering, and I will run this first part. Here we are just creating a variable and using a calculator to apply clustering algorithms using Python. So let me double click it and show you how it works. Here we have this variable which we just created. It's called hierarchical clustering. And we have the 5 chemical variables we already discussed. You see the locker here because we don't want to write on top of these variables. We only want to write on the hierarchical clustering variable, which is the empty variable that will receive the results. So in the calculator, we have 3 spaces to write code. We have the initialization code. So it means that before anything is added, we run this. And in this initialization code, usually we will import the packages we are going to use. We will define the functions and classes we are going to use. Then we have the code itself. So this is the most important part. So this is where we will actually run the calculations. And then we have the finalization code where you can finalize everything. You can close all the open files. You can save all of the files, but it is optional. You can do this inside the main codes. So here we are importing pandas, the standard scalar, agglomerative clustering, dendrogram, matplotlib, and we create this function plot dendrogram, which I just took from the sklearn documentation. You can see the link here. So this is our initialization code. Then I'm transforming this calculator into a pandas data frame. This step is optional. Usually, I do this because all of the documentation for machine learning is based on data frames. So it makes it easier to follow and to copy and paste parts of the code. But it's optional. You can work in NumPy array basis, since every time you read something from your project in a calculator, this object, this variable, will be read as a NumPy array. So here we first create the data frame, then we scale the data. So this is the exact same code you will find in any example for hierarchical clustering analysis using Python. Then we run the agglomerative clustering. I select a number of clusters equal to 3, and I'm saving the labels into this variable I just created, which I'm calling it by V7. V7 is the alias. We can change the alias if you want. And then we do the same thing, but for creating a dendrogram. To create a dendrogram, we cannot define a number of clusters, neither a distance threshold. So it's like the same thing, but just to create the dendrogram. Then we plot the dendrogram figure, and that's it. We finish this step. So now let's have a look on what we saved in our project. So we have this new folder called clustering. Inside this folder, we have the dendrogram. And the dendrogram will show distances in the y-axis and each of the samples of our data sets in the x-axis. So here we have 256 ticks, which represents each of the samples in our data sets. And this figure, this dendrogram, will summarize the clustering process. So how the algorithm merged the samples into clusters, then the clusters into big clusters until we end up with a single cluster. And the y-axis represents the distance between these clusters. And note here that this distance is not Euclidean distance in the x, y, z space. This is distance between the variables, distance between zinc and lead, zinc and chromium, chromium and cobalt. And let's see how it looks in a map. I will just drag and drop this window here. Let's go on your data tree. Now inside the data, we have this new variable called hierarchical cluster. This is the variable we just created and then filled with the results from the agglomerative clustering or hierarchical clustering using sklearn and Python inside the calculator. So let's drag and drop this to the 3D viewer and have a look. So we have 3 different clusters because we set the number of clusters equal to 3 during the hierarchical clustering algorithm application. As we can see, the result is very imbalanced. So we have a lot of blue and just a little bit of green and orange. And as we discussed, we have very noisy results that are not very geologically realistic. So we have these dots of orange and green samples inside of this big blue ocean of code 0 samples. And this might happen it doesn't happen every time, but it's very often that we have this type of results when we apply clustering techniques without taking into account the location of the samples or somehow including in the algorithm this spatial sense. Now let's have a look at the clustering algorithm we have in ISERIS-NEW. So in ISERIS-NEW, we have the geostatistical hierarchical clustering. This is a modification of this algorithm, the hierarchical clustering, but considering the position of the samples. So let me double click it, and we can see the user interface for this task. So the geostatistical hierarchical algorithm in ISERIS, it can do different tasks. It can classify as clustering, but you can also classify new samples. So you can first cluster your data, define groups, define domains. Then this task will train a classifier on this classification. And then when new samples comes in, where you only have chemical analysis and not the labels, not the geological logging, you can use this trained classifier to predict these new samples. But in this case, we are only interested in creating a domain variable. So we select what we want, the mode of the algorithm, then the input data, which is the data we imported as a CSV, the name of the variable we are going to create. So we are going to create a GHC class variable. And then we have a summary on what variables we have in our data and the domains we are going to create. Most of the tasks in ISERIS-NEW, they are like a wizard. So you can click next, 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 and finish. And this is not an exception. So we can click on next to go to the next step. Let me make it bigger. Okay. So in the second window, under geostatistical hierarchical clustering, we will select the variables we are going to use for the clustering. Here I select all of the chemical variables, so zinc, lead, copper, chromium, cobalt, and cadmium, and we can apply a weight to each of these variables. So we can set a higher weight to the geometallurgical variable if you want to produce geometallurgical clusterings, for example. We can also mix continuous and categorical variables for the geostatistic hierarchical clustering. Here, we are not going to use categorical variables, only continuous, but know that you can do this and you can add some weights and relationships between different categories for categorical variables. Then we have some more options here. We need to give some weight to the position of the samples, to X, Y, and Z. The default parameter here is 30%. So as soon as we increase this weight given to the position, you have more spatially structured results, clusters, but we will separate, we will degrade the separation in the chemical variable space. So we have more connected clusters, but less separated in terms of zinc, lead, copper, chromium. So this is a balance between spatial continuity and separation in the chemical variables. Here we set the number of domains and the minimum number of samples per domain. So we don't want domains with only 3 or 2 samples. It doesn't make sense. We want to define stationary domains. We want to use these domains to produce our estimation. So we need at least 5 samples for this. We can set this up, or you can increase or decrease this number based on your specific application. Then we have a very important parameter here in the geostatistical hierarchical clustering, which is the connectivity. So the idea here is, before doing anything, we will connect the samples. So we will create this network of connection between all of the samples. And then we apply the hierarchical clustering, but only samples that are connected can be merged into a cluster. So this is the key difference between hierarchical clustering and geostatistical hierarchical clustering. The idea is the same, the spirit is the same, but you will only merge samples into clusters and clusters into bigger clusters if they are somehow connected. So we have to define this connectivity between the samples. You can use the default neighborhood. So if you hover your mouse on top of this option, you can see that this is 8 infinite splitted sections with 1 sample each. So you mean that for each samples, it will create this 8 angular sector in the sample and will connect in 1 sample per sector, if it finds this sample, of course. If you do not use default neighborhoods, you can create your own moving neighborhood with orientation, size, number of angular sectors, maximum number of sample per sectors, and so on. So you can go simple with default one, or you can create your own customized moving neighborhood. You can connect 1 samples to 100 samples. You can connect 1 samples just to the closest one. You can connect 1 samples to the closest 20, and so on. So it's very customizable in this sense. We can add some sense of anisotropy for these distances. So the connectivity will take into account not only the distance between the samples, but the anisotropy ratios we define. And we can define the colors for the domains and the names for the domains. I will click on Show Connectivity Graph because I want to see how samples are connected. But as soon as I click Next, software will do the calculations. It will say, all right, I found some domains with less than 5 data, so I will ignore them. This is what we want. Et voila, this is the result. So here we have the samples, how they were connected. So we can see all the connectivity between the different samples. This is the connectivity network we defined. We can see box plots of every continuous variable in the different domains. And we can see that, in fact, there was some separation. It's very clear. For Chromium, it's very, very clear. We have this domain 3 low grades, domain 2 medium grades, domain 1 high grades. We have some overlap in some of the variables, but in general, we are indeed separating. We also have the dendrogram, the same thing we saw for the hierarchical clustering we have for the geostatistical hierarchical clustering, since they work quite in the same way. And as we discussed, if you want a better separation here, you have to be more relaxed in the spatial continuity, in the weight given to the coordinates. Okay, we can finish the algorithm. I will close this batch file window, and I'm showing you how it looks. So this is the GHC clustering. And as you can see, we have 3 domains because we defined these parameters at the beginning. And we can see that the results now, they look way more continuous, way more realistic in a geological point of view. We don't have this, first, we don't have this very imbalanced results. Then we do not have this isolated samples, isolated dots inside the big blue domain. So now we have something that indeed look realistic. And we see that the chemical variables are separated in low, medium, and high grades in these different domains. Now let's see how to apply regressor and classificators inside these areas. So I have this batch file called model training. In here, what we are doing is first creating the folders we want. Then let me show you the training classifier. So very similar to what we did for clustering. We have a calculator, we grab the variables we want, we import the packages we want, and we run the Python code, the same Python code you will run in your Jupyter notebooks, the same Python code we found in the millions of examples we have on the web. So it's just exactly the same thing. There's no need for any adaptation. So we transform into a data frame. We define X and Y. So here is classification. So rock type is the target, and all of the chemical variables are the variables we are going to use to train. We split the data in train and test, stratifying by rock type. We scale the data. We save the scalar. This is very important because we need to use the same scalar we used in the input for the data we are going to apply our machine learning model. Here we are using random forest, but we can use any other algorithm we discussed in the theoretical part. So we are using the random forest classifier to create the object and feed it and train it. Then we have some results. We plot some validation results that we are going to see in a minute. And we also save our model as a job leap. So the idea here is training the model, save the scalar, and save the model itself. We are using the job leap format. It's a binary format, very optimized for Python and NumPy arrays. So we are saving in job leap formats, and then we just load this trained model and apply it. And we did the exact same thing for regression. But this time, our target is metallurgical recovery. So same thing. We split, train, test, we scale, we fit the model, we save the scalar, we save the model, we save the validation results. So let me run all of this. Okay, and let's see the project folder. Now we have this model training folder. Inside of it, we have a confusion matrix showing the validation results of the clustering. So we are very good for test 0. We are hitting 88% of the estimates in the test set, 58% on 1, 42% on 2, and 24% on tree. So definitely not a very good classificator, but we only have 256 data, so we cannot expect very good results here. In real world application, we will expect way better than this. And for the regression, we have the same thing, but now we are seeing a scatter plot actual predicted. So we have a R-score of 0.87. The slope of regression is very close to 1. So yeah, I think this is an acceptable result for our regressor. Very important to validate the model, not only showing accuracy, but showing the confusion matrix, not only showing the correlation for regressors, but showing the scatter plot true estimated. Now let's move on. Now what we want to do is to apply these models we just trained. So we are going to apply our classifiers to predict the rock type, and we are going to apply our regressor to predict the geometallurgical variable metallurgical recovery. This is a very important part, and this step is very often misunderstood, and people will often do the wrong thing here. So we don't want to apply our regressors or classificators in estimated models by kriging, because kriging will smooth the data. Kriging will reduce the variance. Kriging will change the correlation. And these machine learning algorithms, if they were trained on the data, they will expect the exact same distribution, the exact same correlation it saw in the data. So if you krig, you don't have the same thing. So you are training on bananas and applying on oranges. So this is definitely not what you need to do. What we want to do here is to apply these models on simulated models, because simulated models, they will reproduce the same variance, the same distribution of the data, the same spatial continuity, the same correlations. So we are co-simulating all of the chemical variables and applying the models on it. Here, I'm not using classical co-simulation. The classical co-simulation algorithms, you need to model your direct and cross variograms, but sometimes the classical co-simulation technique will not reproduce complex correlations. So we are using PPMT, which stands for projection, pursuit, multivariate transformation, to decorrelate the data, ensure that the distribution is multi-Gaussian. Then we simulate the PPMT factors, and then we back transform, and we have the exact same correlation that we have in our data. So in this batch file, we are first PPMT transform the data, then we are automatically fitting a variogram. I'm not losing time fitting the variograms. Then we simulate in the grids, and then we back transform. So this is the variograms that were automatically modeled for the 6 different chemical variables. Now we need to validate our simulations. I told you that simulations will reproduce the distribution, reproduce the spatial correlation, reproduce the correlations, but we need to check this. We can't just simulate and blindly trust that simulations are good. We need to reproduce your data inputs. Otherwise, you are not simulating. You are playing with your data. Simulations must reproduce the data characteristics. After running simulation validation, we have here in the chart files the validation results for cadmium. We can see that the histogram is reproduced, swath plots are reproduced, variograms are quite well reproduced, and the same thing for all of the other chemical variables. This simulation validation tool, it is very easy to use. It's very intuitive and makes our lives way easier. Okay, now last step is to apply these models and check the results, of course. So here in the last calculator, we are applying the classifier, applying the regressor, and checking the results. So let me just double click and show you how the calculator looks like. So again, it's the same thing. But notice that now our data table is the grid. So first we train in the data, we simulate in the grid, we apply the trained model in the grid. So we read the simulated variables and we write the rock type. So we load the scaler, we scale the data, we load the classifier, we apply to the data, we write the results. And this is exactly the same thing we are doing with the regressor. We read the data from the data tree, the simulated data. We read the scaler, we apply the scaler. We read the regressor, we apply the regressor. So let me run this full batch file because we are running out of time. Okay, good. So let's have a look in our grid. Let's see one of the realizations of the zinc variables. So we made 10 realizations for every chemical variable. So this is 1, 2, 3, 4, 5, and so on. We apply the classifier to get the rock type variable. So let's see it together with the data. Okay, so there we have it. We also have 10 realizations. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. And we did the same for the metallurgical variable. So let me put the metallurgical variable here and the data on top. Voila. And we also have 10 realizations for the metallurgical variable. So we are not estimating, we are not simulating it directly. We can simulate it directly, but we do not have enough data to produce a reliable model. So this is why we simulate the chemical variables where we have a lot of data and we can produce reliable variograms and reliable models. And then we apply our machine learning algorithm, our regressor that we know that works well because we validate it to generate a map for the geometallurgical variable. And at the end, we must check with if the results are making sense. So here on the left-hand side, we are seeing the correlation matrix between the data points, and on the right-hand side, we are seeing the correlation matrix for the realization number 1. And we can see that the correlations are quite well reproduced, 83, 88, 42, 49, 0.01, 0.2, 0.56, 0.58. So the correlations are quite close to the correlations we are seeing in the data. And this is what we expect from a multivariate geostatistical model. We want the same distribution as we see in the data. We want the same variogram we see in the data, and we want the same correlation we see in the data. And a very important aspect is what your machine learning model sees in the training process is what we need to see in the applying process. So if you are training on the data and applying on Kriging, your models will probably be very, very, very biased. So it's already 12. And it's good because I just finished what I have to say.